So last time we did some examples of finding antiderivatives. We did a good range of examples here. And so now we're going to transition into solving differential equations, which is really going to be grounded in the finding of the antiderivatives. We're just going to kind of phrase the questions a little differently, introduce some new vocabulary, and then we'll actually be solving for a C. So that's kind of the new part besides just the vocabulary and kind of the way the problems are phrased. All right, so in its most basic sense, if you look at this example, y prime equals 1 plus e to the x plus 1 over x, this is an example of a differential equation. So in a really basic way for our purposes here, a differential equation is just going to be, oops, I did not want, oh, my pen got that thick. It's simply going to be an equation with a derivative or derivatives in it. So it could have a y prime, it could have a y prime and a y double prime in it. But that's an example of a differential equation. So an equation with a derivative or derivatives in it. Now, if you're asked to find the general solution, so the general solution is going to mean they want you to find the original equation. So we want to find that original y equals whatever that is equal to, and then in terms of this plus that arbitrary constant. So let's take a look at this example here, and let's find its general solution. So let's say, first of all, suppose that we are looking at here just to kind of, so here's the example, just kind of highlight that real lightly. So here's the example portion that we're working on. And so now we're going to find the general solution of this example that we're working on here. All right, so if we're at the derivative and we're trying to get back to the original, we're going to be doing the same thing we were doing last time in terms of the mechanics, which is finding the antiderivative. So the antiderivative of 1 is 1x. The antiderivative of e to the x is e to the x. And the 1 over x, that's the one time, remember, you don't bring it up as x to the negative first and try to do power rule because you would be dividing by 0. So that's the one. You'll maybe do that occasionally, and then you'll remember. This is our natural log of the absolute value of x, and then plus that arbitrary constant. So this would be the general solution. All right, so in some ways, nothing new, just phrasing it differently. Like here's a derivative, and now go backwards and find the original. And so you're still finding the antiderivative, just kind of, instead you're starting with a y prime and you're going back to a y. All right, so then you might be asked to find the particular solution. So this still means you're going to be trying to find the original y equals whatever it is, dot, 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 dot. But now you are going to have a specific number for that value of c. So that's the big difference for the particular solution. So in order to find that, they have to give you some sort of point that satisfies the original equation. And so in this example, we are told to find the particular solution when x is 2, y is 12. And we are looking for the particular solution in this example. So what that means is we are going to sub in that point 212. So we are going to have in for x is the 2 plus, and then e to the second, plus natural log of the absolute value of 2 is just 2, plus that arbitrary constant is equal to the y value of 12. And so we are simply solving for C here. So we just have these constants to subtract over to the other side. And so we now know that, scroll up here a little bit, C is equal to 12 minus 2. Let's go ahead and actually make that 10, sorry. So 12 minus 2 is going to give us 10. And then minus e squared minus natural log of 2. So not the nicest looking constant, but still just an arbitrary constant there. We're going to leave it in its exact form unless we're prompted to go to decimals. And so the particular solution here is going to be y equals x plus e to the x plus natural log of the absolute value of x plus, and now this is my c, 10 minus e squared minus natural log of 2. So that is our particular solution. All right, so that's going to really be kind of the new part here, is solving for a specific value for C. So there could be some that are like this example that are just kind of in general, just kind of, given some equation, not put into any particular application. But one place where this is really important is going to be in application problems. So we're going to do just that now. We're going to take a look at a couple of examples with applications. So in our first example here, it says the growth rate of seeds that were planted at a height of 15 centimeters is given by dH/dt equals 1.4 t plus 5 centimeters per year. Now, one thing I would just kind of point out here, there's a lot of things that indicate, even if they hadn't labeled this as a derivative, just kind of be aware here. They're telling you it is a growth rate. The label is centimeters per year. All those things kind of go into, even if, like, let's say this hadn't been labeled as dH/dt, if I see the growth rate and I see a label of centimeters per year, that is telling me how much the height is changing, centimeters, with respect to time in years. So you should be kind of prepared that not every problem will necessarily be labeled as a derivative. This one is, they might not always be. All right, they sell this plant after 8 years, and the question is, how tall are they when they are sold? So the goal here, if we kind of think about the question that they're asking us, I mean, if I think about this final question, my goal is to determine the height. Like if I had a height function, I'd like to know the height after 8 years. That is my goal. But right now I don't have the height function. What I have is the rate of change. I have the derivative of the height function with respect to time. So what we're going to do is we are going to start with that original differential equation here and say, okay, well that means if my dH/dt, I'll just recopy it here, is 1.4 t plus 5, that tells me that h of t is going to be our 1.4 t squared over 2 plus 5t plus our arbitrary constant. That's crucial because I need to evaluate h of 8. I need to figure out what this c value is. So we started off and we said, okay, we have this differential equation. We can solve it for the general solution, but now I need to find what this c is. Well, that means I have to have some sort of ordered pair on this function. Well, here's what I know in order to find that c. I know that they were planted at a height of 15 centimeters. So this is going to tell me that h of 0, being the time that these trees or whatever they were planted, they had a height of 15 centimeters. And so that is going to tell me that I can sub in Of course, the 1.4 divided by 2 is just going to be 0.7. But I can sub in my 0 for t. So sub in 0 for t. And then I can solve and set that equal to 15. Now this is why these problems are sometimes called initial value problems, because a lot of times if you notice here, when you actually solve for t or c, of course, these first two terms go to 0, and you're going to get that c is equal to 15. And so a lot of times when they give you this initial value, they sometimes call these initial value problems because they gave me the value that it was initially at time 0. But you need to be careful and not fall into the trap to always think that whenever they give you 0, that that's always going to be what the c is. This is true of polynomials, but you start to throw in log functions, exponential functions, like e to the 0 is not 0, it's 1. So if there was an exponential term in there or some other type of term, you need to be a little bit careful with that. So in any case, when it's a polynomial, if they give you something at time 0, that will actually be your constant. So here's what we now know. We now have, so we now have the particular solution. So h of t is 0.7t squared plus 5t plus 15. And so once we have that, we have everything we need to answer any question about the original function. So we can now answer our goal here, which is simply to figure out what is h of 8. So we would just sub that in. And so this comes out to be, actually, hold on. I thought I had that done ahead of time and I didn't. 0.7, just real quick on my calculator here. Let me type this in. Actually know approximately about it. This one came out to be 99.8. So this was our 99.8 centimeters. All right, let's look at one more here in this video. Number 2. So this one says a ball is thrown upward from a height of 4 feet with an initial velocity of 71 feet per second. Find its height at any time t if acceleration due to gravity is negative 32 feet per second squared. So my goal in this one, is simply to find the original position function. So I'm just trying to find what a lot of times we call s of t. All right, so let's start with what we have here. And we know that the acceleration function here is simply going to be negative 32. So we are going to work our way backwards. So the thing that you have to kind of recall here, so let's just write this off to the side. So from the very beginning of this semester, we know that if we start with a position function and then we take its derivative, we get to the velocity function. And if we take its rate of change or its derivative, we get to the acceleration function. Now we're going to go and have the ability to go into reverse here. So now if we have any of these functions, we can kind of move in between them by taking antiderivatives. So if I am at the acceleration, I can take the antiderivative in order to get back to velocity and its antiderivative to get back to position. All right, so let's get back to the specifics here of this problem. So we're going to take this antiderivative, and so the velocity is negative 32t plus an arbitrary constant. Now, a lot of times with these problems in particular, you're going to see this arbitrary constant written as a v sub 0. Gives it a little more meaning. It represents that initial velocity. Now, we need a point on the function in order to be able to find what this v sub 0, or this arbitrary constant, is? Well, here's what we know. We know that the initial velocity is 71 feet per second. So we know that v of 0 equals 71. Well, once again, if you sub in 0 for t and solve, I mean, certainly do it if you're not sure here, but I'll just kind of put this in parentheses. So if you have negative 32 times 0 plus this arbitrary constant equal to 71, that is certainly going to imply that, in fact, I'll just kind of show it and just say, okay, so that's obviously gone. And so obviously here your c is going to equal that 71. So again, when you're given this 0 as your initial condition, as long as you're dealing with a polynomial function, whatever that value is, it will be your c. All right, so here's what we now know. So we now know that v of t is equal to negative 32t plus 71. Okay, so we started with our acceleration. We now have velocity, and we now need to take its antiderivative to get back to the position function. So s of t is going to equal negative 32t squared over 2 plus 71t plus, again, an arbitrary constant, which a lot of times in these problems, this is going to be referred to as s sub 0 to represent its initial position. So this initial position here, that means that we need some points on the original function in order to figure out what that constant is. Well, here's what we know. It was thrown from a height of 4 feet. So that is its initial height. So s of 0 equals 4. All right, so again, I'll just kind of put this work in parentheses, but certainly if you take your negative 16 times 0 squared plus 71 times 0 plus your arbitrary constant and set that equal to 4, obviously your c here is going to be 4. So we now know that our height position function is negative 16t squared plus 71t plus 4. And that was really the whole goal of this particular problem. Now, what I want you to notice in general after we look at this problem here is the following. Okay, so let me just get a straight line here. All right. So let's say, so in general, and a lot of you physics students in particular already know this and are probably bored to tears as we kind of go through this example, but here's what I want you to observe. There was nothing really special about the 71 or the 4. Those were just the specific values that we ended up with. So here's what I want you to observe looking back at this problem. The 71, there was your initial velocity, and that's where it ended up. And your 4, that was your initial height, and that's where it ends up. So here's what I want you to just kind of pull all this together and to observe. So in general, if acceleration due to gravity is negative 32 feet per second squared, or if you're in meters, it's the negative 9.8. Didn't leave myself a lot of room here. Hold on. Let me rewrite that. Or A of t is equal to negative 9.8 meters per second squared. What that is going to tell you then is your velocity is going to be negative 32t plus whatever your initial velocity is. Or if you're working over here, your velocity would look like negative 9.8t plus whatever your initial velocity is. And then your position function, s of t, is going to be negative 16t squared plus that v sub 0 times t plus whatever your initial position is. Or, again here, the negative 9.8t squared divided by 2 would be negative 4.9t squared plus v sub 0 t plus s sub 0. So as you look at those, think about this v sub 0, like in the last example. That's just your initial velocity, whatever that might be. And then your s sub 0, that is just your initial position. Okay, so those are important observations to make. Okay, so when we come back next time, we'll wrap up. We'll just look at another example or so of these differential equations specific to the motion problems.